So hello, now I'm back and I'm gonna wrap up a little bit the model-based testing section of the course, and then I'll bridge over to some of the parts in part 3 before we wrap up the course in a few weeks. So today, now you've seen model-based testing in practice, this type of modeling, how you can drive testing based on that. So today I'm gonna talk a little bit about Simulink, which is a very well used and a much used simulation and also nowadays development and testing environment for, let's say, control engineers, but also more and more software engineers and so on. So for embedded cyber physical systems and so on, this is one of the more prominent model-based development and testing environments. So I must first say that I'm in no way an expert on Simulink. So I'm going to go through with you today a little bit a paper which talks about one way of testing Simulink models, and we'll explore the paper together. So it'll be a slightly different module in that sense. There are no slides per se. So first, I found this good introduction on what is Simulink. So I think this is from University of Oxford, course notes, an introduction to using Simulink. So it's by Eric Peasley, Department of Engineering Science. So you see here already that it's control engineers, machine people. For example, my cousin, he works in Volvo. And a few years back, when he was more into motor development, so developing the engine of there, they use Simulink a lot to simulate the engine and actually generate code in the end, C code from it. So what is Simulink? It's a visual programming interface in a sense, where you can model systems and you can control systems, and in the end you can sort of output C code or binaries in the end, and actually download to your embedded system and run there. So it's nowadays it's used in many different phases of development, and now with your new knowledge on model-based testing and modeling, we can look into a little bit what is this from our perspective now, from a model perspective. What is this? So these programs, Simulink models or programs, they are visual, but they are a model. So you have nodes, you have connections, edges between the nodes, and you have computation going on in these nodes. So of course you can develop any program in this. And then it becomes important, how do you test this? And in particular, because this is used often in safety critical applications, like driving a car and so on. So you have nodes, and they can have mathematical functions. So you have a library when you start up Simulink of different types of nodes, and you can also add your custom nodes. But often you will build up a more complex node or a block of nodes to be a certain mathematical function or some computation, and then you do that from basic elementary operations. So here you can see there's some kind of calculation, so you have some external input to this force actuation here. So you have time, this comes from some clock, hardware clock in the end, I guess. You have some measurement, external forces, some kind of sensor typically here, creating input, and then you have two inputs to this block coming from the older time steps of the same program. So this is typically what you see in control programs like this and models. So you get time, some kind of external sensor measure a position and a velocity. And then this block here has some kind of mathematical function that calculates a force. So in some way this is some kind of control algorithm so you can control an actuator setting a force on the brakes or something like that. And then depending of course on the mass, the force will have more or less effect. So this block is trying to calculate what kind of acceleration do you get if you apply this force. Say the engine is applying force, the mass of the car, and then you can calculate the acceleration, and then you can integrate that acceleration and get a velocity. So this is over time, this will accumulate acceleration values so that you can estimate the velocity, and if you integrate that in turn, you can get the position. So this is like Newton's laws implemented here in a simple Simulink model. So that's just one example, right? What I wanted to share with you today is this paper. So these are some colleagues of mine. So I work quite heavily today with Xin Yu. He's no longer in London, but he was with another colleague, Mark Harman, who has a big group there, very well-known researcher. But Xin is a great guy, and he's now back in Korea, South Korea, where we work together on testing of neural networks and other things. But a few years back, they did this interesting paper on transition coverage testing for Simulink/stateflow models using a messy genetic algorithm. Why I wanted to go through this paper with you today is because the messy genetic algorithm is an example of a search-based testing procedure. So we will not go into detail about this today, but I will mention that in the module before the end of the course. So search-based software testing is one of the sort of hot areas of automated testing. So it's quite important that you understand what that is. But for today, you can just view it as a super efficient search. So it can search for test data. Here they are going to use this to try to cover a Simulink model to test it. So a particular form of coverage. You know, we discussed in part 1 the importance of coverage measures. And here we can see that when we have a coverage measure, we can use that to ensure better testing of a Simulink model. So that's kind of the setting. Let's go through a little bit here. So they introduce it's a fairly short paper, so the abstract is very short. But here they say we introduced the messy GA. So it's some kind of search-based algorithm. You don't need to know the details now. And here's the purpose of using this, is transition coverage of Simulink stateflow models. So this is about how can we better test these type of models, right? So we introduce a tool that implements our approach and evaluates on 3 benchmark embedded system Simulink models. And they achieve, of course, better coverage when compared to other techniques of generating data. So one is commercial tool for testing of these models. Another one is a random search. So that's the setting. They go through here and mention the importance of this type of system and the importance of Simulink. And then here they say Simulink stateflow. So they, Simulink is a commercial variant, but it's built on older languages like stateflow and so on. So they consider it the same. I mean, intellectually, logically, it's very similar. So they say it's one of the most popular modeling languages in the automotive and aerospace domain. That's still true, especially in automotive, but in control type of problems. Simulink is a software package for modeling, simulation, and analysis of system-level design features of dynamic systems. So that's the typical thing, that something is moving, you have sensors, you have actuators, and you want to control this with some kind of software. Then you can model it in Simulink, you can simulate it in your computer in Simulink, and you can also test and compile it into code. Models can be designed hierarchically, so that you have this thing that you can have a block in a high-level diagram, which in turn is implemented by a more detailed model on a lower level. So you get a hierarchy of these models. And each model consists of connected blocks. So these are blocks are computational nodes. So it's in our old terminology in the course, it's a node, a block that makes a calculation. So it's a functional unit, a function in traditional programming language. And Stateflow allows event-based modeling. So that's the addition of Stateflow here. You know, we're not going into the details here. I want to show you the general ideas. So they have one example. Let's look at that. So here's a more complex one than you saw on the previous paper I showed. So here's the main model, and this one here is in a hierarchy, because this one is expanded. This one expands into this, and here you have, now we're getting very close to the type of finite state machines. You know, you see the same type of structure that you've seen in the modules in the assignment. So you have some kind of state, and then you have transitions between these states, and they have conditions on them, so something will happen. You know, something needs to be true before the transition happens, and you can also have like actions sometimes on these transitions. Anyway, in this paper, how are we going to test this? So what we want to do, one goal we can have in testing these type of models, is that we want to ensure we want to run the fewest number of test cases and still sort of cover all these transitions, right? Here's quite a few, and here are a few others. Of course, as we discussed in part 1, I mean, coverage is often not enough, but it's a start, right? So they want to cover the transitions. That's a starting point for basic testing of this. And they say there are 2 challenges. So the first challenge in testing these type of Simulink models is an operational semantics of the blocks, Simulink blocks, such as discrete time integrator block in figure 1. The integrator block is often used to integrate or accumulate signals. Some transition triggers may require these blocks to accumulate a specific amount of signal before they become activated. So let's see, here is the discrete time integrator. So what they are saying here is that a challenge is that if you only give one input and run this through once, this has a time behavior which you might not activate, right? And which is hard to predict, because this is part of the loop here. And this is an integrator, so it will accumulate multiple values over time and do some calculation on them. So this is a challenge. How do you select good inputs for testing this when you have these, could be very long time behavior here, right? So this makes it a little bit complex. You cannot consider the static model. You have to consider what happens over time. So that's a challenge here. What's the other challenge? The second challenge is the existence of cyclic paths. So this is related in a sense, but in the model, the trigger for transition 17 requires hit to be 0. However, the only way of reaching the source state 6 is to go over the cyclic paths between state 3, 5, and 6 twice. Okay, so this is probably too involved for me to show for you here now. I linked to the paper, but there's some kind of complex dependency here. So let's see if we can find at least some of them. So the trigger for transition 17, let's try to find 17. Where is that? I don't see it. Here it is, right? So to go from this node here to over transition 17 to the state number 7, there's a complex set of previous transitions that you need to go through. So, you know, you have this in all types of software testing, of course, that there's like complex dependencies in the state, or and then setting up the inputs to enable this to happen. A specific goal that you have is going to be complex. Yes. So these are two main challenges. They say why you need a stronger method than just random testing here. And then they say, okay, then they describe their method, which we don't care so much about right now. And they have also written a tool for this, and they've tested it, of course. So then they go into definitions. We don't care so much about that now. That's the formal part of the paper. Here you can see a simple model, a simple state flow model. So Here you see you're very close now to the extended FSM or something like you've seen in part 2 of the course. So you have nodes, they are numbered, they're named somehow. You have conditions on what needs to happen to take a transition, and now you want to do good testing of this. And so the idea behind search-based testing is that you randomly generate some test cases, you run them on the code or here on the Simulink model, and you measure what kind of effect did you have. So which transitions did you go take when running this example, this randomly generated one. And then you look at this. Okay, so maybe I covered 3 different transitions, but my goal was to cover something else, right? So you measure the distance. What did I actually cover to what did I want to cover? And if you have generated, say, 100 different inputs, and you measure the distance to what you want to achieve, some of these 100 inputs are likely to be a little bit closer to what you wanted to achieve than others, right? So what a search-based procedure does is that it selects the best ones among these 100 and it mixes them together. And the idea is, as long as I'm getting closer to the goal, I will keep on trying, in a sense, until I fulfill the goal. And I will take the things that are closer to the goal as more likely to lead to the goal, right? That's basically the key idea there. And this turns out to be a very generic technique. So in every generation where we're going to create new inputs, we take the best ones from the previous generation and we mix them up with some randomness added to it. But it's not a random search. It's smarter than a random search because it has this filter of skipping the bad ones we found and focusing on the more promising ones, the ones that are closer to our goal. So here our goal is transition coverage. So you can imagine that if we want to cover number 17, what kind of metric of distance to reaching this goal can we have? Well, we can look at the source node for 17 and that one. And then of course, logically, if we want to make this transition happen, 17, we have to first be in this state. So a sub goal is to be in this state. And then we can backtrack from that. So any random test that we test during our search that end up here are more likely to take this transition than others. So that's one thing. We can also count transitions that lead into this state. So if we take transition 16 or 14, and that's good. But if we take transition 2, which skips 17, then we should detract. We should say now test cases that take this one are now more distant because they are not taking us closer to our goal, right? So taking this one, that's good. Taking this one is good. Being here is good. Taking this one is bad because that's not what we want. So we add up these different things and we can go on to the next one and we can do like a little bit penalty if you take the wrong choice here and so on. So this is the way you do it. That it's basically an informed or smarter way of trial and error, right? But it tends to be working pretty well, search-based testing. And this is the whole idea of this paper, is then they actually build a tool to measure this coverage and to guide the search so that they can then cover all different transitions here. So let's look at some details. I mean, I don't need you to understand all the details of this paper, but let's look at some results. Here's their test data generation framework. Let's look at that before we go to the results. So what do? So they have a coverage goal generator. So this is exactly doing automatically what I described to you. So it is generating the goal for the search, right? So maybe the goal now, let's say we've covered most of the transitions, but 17 we didn't cover yet. So that's this goal generator will say, now my goal for the search is going to be to cover 17, and then it's going to analyze the Simulink model and say, okay, so what is good if we want to get closer to covering 17? It's those things that I told you. So taking these two transitions, not taking that transition, being in that node that precedes 17 is going to be important. So you see here, it takes the model, which comes from Simulink or your development. It analyzes that, what's the goal right now for our testing. Then it creates the coverage goals, and this is going to be used in the test case generator. So, and here on top in the solution, they take also the model, and they have, of course, a way to get an executable model from that model. So you would buy this from MATLAB, a Simulink simulator or executor. And then the search will be to generate test cases, try them on the executable model, get feedback, so measure how close are we to fulfill the goals, and then this loop will go on and on and on. We'll refine the test inputs until we hit the goal or are very close to it. And then we create test cases as the output of this. So what kind of results did they get? They tried it on fairly small systems, but you have to start somewhere. So the number of states, the biggest one had 15 states, 19 transitions. And here they compared their approach, the MGA, to a random testing approach and to the commercial tool Reactis. I don't know it, but anyway, some kind of tool focused on this. So let's take the biggest model. Well, here you see that Reactis cannot handle even 15 states and transitions, so it's probably based on quite old technology, this commercial tool. Random, of course, can generate, can handle anything. It doesn't have any assumptions. You just need to be able to generate the input data in of the right types. So what do we see? Maximum coverage for random was 85-86%, and for this search based you get 100%. So and then success rate is important. Is how many times, if you start it 100 times, 90% of them it will reach 100%. So random is, it has no success rate because it never reached 100%. And you see the means are quite different here also. Almost always their solution will create 100% coverage, 98.5 in general. And for this other example, you had 96 in general, random was 86, and here the commercial one was okay, and here also similar. So it seems the indication is that this technique, the search-based technique, can handle larger models than existing solutions and in a better way than random. Anyway, this was just one example. So Simulink, we can't go into the details this year of the course, but I think given the knowledge you already have about model-based testing from part 2, you can easily adapt to, you will, when you go and work with these things in industry, you will see many types of models and model-based testing. UML is the other big one, so probably I'll do one also looking at a recent result on testing in models and UML models. Okay, that's it for this this walkthrough. So and we will talk more about search-based testing in the coming ones. Thank you.